Hello, good morning, everybody, and welcome to this CMCC webinar regarding the domain-specific language for weather and climate modeling. Before starting the presentation, I just give you a brief introduction about the CMCC. CMCC is a non-profit research organization established in 2005. In 2015, the center became a foundation. CMCC, a scientific research center on climate change and its interaction with the environment, the society, the world of business, and policymakers. Our work aims to stimulate sustainable growth, protect the environment, and develop strategies for the adaptation and mitigation of climate change. The center is organized in the form of a network distributed throughout the country, with locations in Lecce, Bologna, Capua, Milano, Sassari, Venice, and Viterbo, which involves and connects public and private entities working together on multidisciplinary studies concerning issues of interest to the climate science. CMCC benefits from the extensive applied research experience of its member and institutional partners, like, for example, several universities around Italy, like the University of Salento, University of Ca' Foscari in Venice, University of Sassari, University of Laustia and Polytechnic of Milan, and also some research centers like the National Institution for Geophysics and Volcanology and the Italian Center for Aerospace Research. CMCC scientific activities are distributed among 9 research divisions, which share different knowledge and skills in the field of climate science. We have a division for the computing, economics, policy, study, simulation and prediction, computing, modeling, impact, adaptation, impact on agriculture, and so on. The main outreach of the CMCC regard to the scientific articles for international journal, educational programs, events, and communication activities for public at large. I also recall the participants that before starting the presentation, they have the possibility to post any question to our speakers. I will read at the end of both presentations. I will read your question to our speakers. So today's topic is related to the domain-specific language that are gaining increasing interest in the weather and climate community. The use of DSL for programming weather and climate models will provide performance, portability, accelerating algorithm development, increasing domain scientist productivity through a high level of abstraction. Today we have 2 different presentations. The first one, I will introduce you Carlos Osuna, who is a scientific software developer at MeteoSwiss at Zurich. He received his PhD in experimental energy physics in 2003. Since 2011, he has been involved in research projects at Zurich, ATH Zurich, and MeteoSwiss to adapt regional and climate simulation model to Cosmo to graphical processing unit GPUs, which led to the adoption of MeteoSwiss for a new GPU-based supercomputing system that run Cosmo operationally. Since then, he has been exploring domain-specific languages as a solution to performance portability of weather models for multiple architectures such as CPU or Xeon Phi. Currently, he is involved in efforts to extend this DSL solution to a wider range of weather models. So I just give Carlos the floor, and Carlos, please, you can start your talk.
Thank you very much, Italo.
Okay, fine.
So good morning, everyone. Thanks very much, Italo, for the nice introduction. It's a pleasure for me to give this webinar on domain-specific languages together also with Rupert. Since this is the first presentation of the 2, I thought we first need to introduce a little bit the domain where we are developing these DSLs for. to have a better understanding of what are the main goals of a domain-specific language. So the domain is weather and climate simulations. The models are typically doing both tasks, weather and climate. And I'm showing here a picture of the particular domain that we run operationally at MeteoSwiss that runs around Switzerland, of course, but we need to cover the entire Alpine arc because it dominates quite a lot the weather effects. Do you see two different products here? One is really the high resolution, and the main message here in this slide is that our field is going towards high resolution, since there are very clear scientific evidence that the high resolution simulations improve significantly actually the scientific results, the quality of the forecast, also together with Going Ensemble. So this we have seen in the past decade or the past years important, significant scientific improvements thanks to this increase of the high resolution. The only issue here is that with this high resolution, the computational cost also increases quite significantly. Typically, when we increase, like for example, from 2 kilometer to 1 kilometer resolution over domain, this implies a computational cost of a factor 8. So we need to prepare for that. And one of the solutions that we have been seeing in the past year is also to adopt GPU systems, so graphical processing units. And here we can see the operational system that we are running at MeteoSwiss. As already announced by Italo, it was the first operational system adopting GPUs. The system is rather small. It's only 2 cabinets, and it contains NVIDIA GPUs K80. Each K80 contains 2 graphical processing units. Beside, in this floor, there is also the installation of PizzaIn, which is, I think right now is top 6 in the top 100 supercomputers of the world. But graphical processing units are clearly one way of addressing the increased demand of computational costs in weather and climate simulations as we go towards a high resolution. Now, the question we started asking ourselves at the time is how to adopt these graphical processing units. They are completely different devices, different chips. You need to program them in completely different ways as we are used to with the traditional CPU in our models. And it's also a daunting task given the fact that a model is typically an application of the order of 100,000 to 1 million lines of code. So it's quite significant if you need to refactor and rewrite an entire model adopting new programming languages. So this is where DSL helps. It's not the only way, but it's one way that is getting quite some traction in the past years. It's getting quite some interest, and there are more and more developments happening in DSLs and adoptions on weather models. So here I wanted to depict the idea behind a domain-specific language in this graph, where we see in the top layer is from the physical processes to the algorithm development. That means first in the process of developing a model, the first thing that the physicists do is to understand the physical processes. In our case, weather is dominated by the Navier-Stokes equations that produce the governing equations of motion. But it's not only that. We also have, for example, external forcing, like radiation. We have the influence of the soil into the atmosphere. These are what are called physical parametrizations. So from this understanding of the physical processes, the physical law, we go into mathematical descriptions. So these are math equations that describe those processes. And the next step is, since those equations, they don't have an analytical solution, we need to solve numerically the problem. This discretization generates some algorithms. And these algorithms later on would go into the top layer of the graph. We need to generate an implementation that solves this algorithm. Now, when we move to the bottom layer of the graph, a particular implementation, we need to adopt already existing solutions. We need to adopt, for example, we need to decide that we are going to implement our model using a general purpose language, like Fortran, for example, which is quite common in our domain. As I already explained, our simulations are parallelized, since running them on a single computer is not enough. We need more capacity, so we need to parallelize our application across a large supercomputer. And there are different programming models that helps you doing that. The only problem is that there is not a single programming model. There are many. MPI is quite a standard, but then it can be combined with OpenSCC, can be combined with OpenMP, CUDA is another programming model. These are just different examples for programming CPUs, GPUs, or other architectures. And on the bottom right, here we have the box of the hardware-specific instructions or hardware-specific implementations, since what we have been seeing in the past is an increasing emergence of new architectures. I just mentioned GPUs, but there were others, and there will be other vendors are also producing their own specific GPU. So this is something that we are being confronted. The fact that our models, they need to be run efficiently now on multiple architectures. And it propagates back. Multiple architectures also mean multiple programming models, but we would like to retain maintainability of our models, and we would like to retain a single source code if possible. Because as I mentioned before, models or applications of million lines of code they are not maintainable if we need to duplicate or triplicate or generate a number of implementations for different architectures. So this is where the DSL helps in providing this separation of concern, and this is exactly the middle layer that we see in the graph. The separation of concern means that we provide a programming model or a language that allows to separate the numerical discretization, the algorithm specification of the problem, from a specific efficient implementation for a given hardware. What this middle layer here provides is just an example in this case of a divergence operator. It's very high level description of it that you can read, and it's quite close to the mathematical, this on-edge sum reduction. The domain scientist could naturally read it, but this is far away from a particular implementation that written in Fortran, for example, can be compiled by a standard vendor compiler. Now, the role of the DSL is to take this description of the problem, very high level like MATLAB, and generates automatically efficient and parallel code that will run efficiently on different architectures. Good. But let me go back a bit, or let me go out of the weather domain to try to explain even better what a DSL is or it can do. And I take just a very simple example, which is a matrix transpose. This can happen in many different domains. It's not specific to weather and climate. And on the left-hand side, what we see is a MATLAB a specification of the matrix transpose, and it's very simple. It has a specific, MATLAB gives you a specific notation for describing that this problem is a transpose, A equal B transpose. Now, if we need to implement this on a general purpose language, you'd see something similar to what you have in the right-hand side. Understanding that this is also a very simple, non-optimized implementation. So an optimized implementation would have to implement much more optimization techniques, and the code would become much more complex. But still, you see that in the right-hand side, first of all, is general purpose. It's implemented based on loops and based on memory accesses. So it can solve actually any problem, not only the matrix transpose, that's the difference to the MATLAB example, but there is no semantic information that you give to the compiler about this is a matrix problem. You hardly actually see a matrix in this problem. While this is the advantage of a domain-specific language, you provide this specific semantic. On the one hand, the code is more readable. On the other hand, you give more information to the compiler to understand how this problem could be efficiently solved in a different architecture. Right. So this is in the genes of the DSL, and then going back to the very same example that I was posting before in weather and climate, this would translate, for example, this high-level specification of the divergence would translate in the code that you see at the right, where this code has been parallelized, this code has been ported to GPUs and CPU at the same time, is very efficient, but it's at the same time less readable and less maintainable. So the goal of the DSL is to be able to provide this language to the user so that we can write in this high-level language and provide a compiler that automatically generates a code that we can see on the right-hand side. This is what these DSLs allow to put this Cosmo weather model in production, and this is just a simulation of one of the outputs that is running every day. The simulation is generated by ETH, and the main message here is that thanks to this also, since the generated code can be very efficient because we can apply many optimizations, we are not worried about deteriorating the readability of the code. This advanced optimization precisely provide a higher speed up as compared to traditional CPUs. In this case, we got a factor 4.4. But now that we have an introduction, we can go more into the details of how a DSL look like. And this is our example. Later you will see the example of a different DSL from Rupert 4. But in this example, what we provide is a language for implementing the patterns that we have in our domain. Many of them are actually stencil computations, what is called an stencil computation. There are many details in this slide, but the main idea we would like to convey here to you is the fact that this is very high level. There are no loops, there are no arrays, there are no the references of memory, simply the equations, and then we describe what we do in our stencil by accessing our neighbors. We can also specify different regions in the vertical domain, for example, and at the same time, we don't need to provide a parallel implementation that will need to take care of data races when we run this example in parallel. Now, the DSL will go through your code line by line, digest it and understand it because it understands the syntax, and it can also generate graphs that later on are used for the different optimizations. So it goes via the Laplacian, the fluxes, the final solution. It builds automatically this data dependency, and then once it has understood your code, it can actually build the different parallel groups so that we can parallelize your code in a safe manner and in a very efficient manner, maximizing the data locality. Now, this is the architectural design of the DSL. First of all, on the left-hand side, we have the front end. The front end is the component that understands your code, but it doesn't do any optimization. It doesn't do anything yet with it. And this front end will generate an intermediate representation. The intermediate representation, we will see more examples from Rupert why we do that. And the main goal here is to be able to interoperate different solutions. Since an intermediate representation is not language dependent, it's really universal. Then in the middle part, we have the DSL compiler, and this compiler contains all the optimizations, all the parallelizations. Our code is initially sequential, and as I explained, line by line, we parallelize the code and we integrate optimizations. And finally, on the right-hand side, we have the code generation, and this code generation is given to a traditional compiler, to NVIDIA, Intel, Cray compiler. We don't compile finally to machine code. We use vendor compilers, sorry. And as the final slides before giving the floor to Rupert, we wanted to show some examples on demonstrations on a real, not just on this prototype, but on a real model, which is the advection of the NEMO operator. I will skip the details of the NEMO. This is the description of the model. It's basically a diagonal on a 3-polar grid. So it uses this syntax when you can reference to left, right, and top and bottom neighbors, grid points. And with this, we could implement the advection operator. And this is the comparison between the original Fortran code that is not parallelized with OpenMP, is not GPU capable, but is running efficiently or vectorizing efficiently because of Fortran. You also see that the loops, they need to be grouped into different loopings, so to solve data dependencies. And on the right-hand side, we see the DSL code, the equivalent one, where a lot of details were hidden. And at the same time, all the groups, they could be collapsed since the resolution of the data dependencies can be, as I explained, done automatically by the DSL. So this is in principle the main idea, that our codes, our models, they will become more readable. And at the same time, this code on the right-hand side, now we can compile it for GPUs efficiently, or we can compile it for, in principle, any architecture, as far as we have a backend that implements this code generation. And with this, I think I'm ready to pass the floor to Rupert.
Okay, Carlos, thank you for your presentation. You've been so clear. Before, just let me to introduce Rupert Ford. Rupert is a computer science at the Science and Technology Facility Council at the UK. He received a Master of Science degree in Computer Science in '99 at the University of Manchester. He then became a founding member of the Center of Novel Computing, a high-performance research group based in the School of Computer Science at the University of Manchester, where he stayed for over 20 years. And in 2012, he moved to STFC, where he continues to pursue his interest in performance, portability, and productivity. The majority of his research over the past 20 years has been undertaken in the Earth system modeling and integrated assessment domains, in which he has developed the BFG coupling system and the Cyclone code generation system. He is currently involved in UK L3 project and co-leads the Future Technology Work Package in Easy Waste 2 Center of Excellence project. So, Rupert, the floor is yours. Thanks.
Thank you, Italo, and thanks for inviting me to this webinar, and also a nice introduction, and thanks to Carlos for giving a great introduction. It helps me a lot, and Carlos and I are collaborating together on this work, so it's really good to be talking together. So this work is the Cyclone software that I'm talking about is not just me. It's a number of people, two of which are in the room with me actually. So myself, Andrew Porter, and Sergi Ciso are from STFC Hartree Centre, as Italo just said. We have Eva, who is from the Met Office, and Jörg Henrik, who is from the Bureau of Meteorology in Australia, and we as five are kind of regular developers of Cyclone. There are many others who have helped and developed and continue to, but we're the main developers. So Carlos has given a very good introduction to this. I'll just quickly go over essentially the same argument. The idea that we want performance, portability, and productivity is seem to be called these 3 Ps now. I think this has come from the States. But my way of thinking about it really is that what we're really after is maintainable high performance software. So we want it to be maintainable. We have very large codes, as Carlos said, and but we also want it to be high performance. And again, as Carlos said, I think one of the key things for this is single source science code. If we start splitting our source into GPU versions and other versions, there's a real issue for maintainability. And when just to point out that when in the 3 Ps where they talk about portability, I think the issue here is performance portability, not just portability. It doesn't mean just running it on another architecture. You need to get performance out of these things as well. And so what we have in our domain is very complex parallel codes which change over time. Quite rapidly actually, and they're running on complex parallel architectures that change over time, also quite rapidly, and then we try and compile these with complex compilers and runtime systems and environments which are also changing over time. So we have a very complex optimization space. And my argument is therefore the likelihood of there being a single source optimized code that works across all of these things is very unlikely. I mean, you may be aware of work, say for example by Kokos, which is trying to do this. So there are some notable attempts to do this. But from our perspective, if you want to get high performance, the solution, or a solution, as Carlos said, is really to look at, rather than going for an optimized single source optimized code, is to actually try and separate out the science and the specification of the science and the code from its optimization, which is essentially the same thing as Carlos was saying in his picture earlier. So for me, there are a number of different potential DSL solutions, and they kind of vary in their view of what abstraction we want to. Well, the level of abstraction. If you go further up, Carlos showed quite a high level of abstraction, and where you essentially replace your existing code and you rewrite it in a better way, and that gives you the most flexibility and high performance. But it also constrains you to use that environment. But the advantage is potentially it gives you the highest performance. And then the disadvantage potentially is that it does require this revolutionary approach. It's not an evolutionary approach. On the kind of the lower level, if you think about existing code, then if you can operate on existing code, then you have a much more unconstrained environment. But you are going to limit yourself with what performance you can get, and the question is how much is this limitation versus going to a higher level. And the other advantage potentially is there's a potential to maybe have an evolutionary approach rather than a revolutionary approach and migrate across this level of abstraction towards higher levels. And that's where we've been sitting. So one of our front ends is called Elfric Fortran code, but we also have higher level specifications as well. So it's a mixed bag of the two, and that kind of sits somewhere in between. But we've also been looking at what can we do with an existing code, and in particular Nemo. So rather than rewriting Nemo, we've been looking at how you might optimize Nemo as it is without changing the code. So Cyclone itself, just to summarize, is a domain-specific compiler because we're sat in weather and climate, and it's embedded in the sense that we are embedded in Fortran. We do take Fortran as input at the moment. We could in the future do other languages, but that's where we sit, and we're in the domain of finite difference, volume, finite elements, and it's a configurable system, so we can have different APIs for different solutions, although it's quite complicated to actually do that. And as I said before, we're currently Fortran to Fortran, but we are looking at doing different backends. So one example is we've been looking at targeting OpenCL recently. For the Elfric API, the one in the middle I mentioned, we support both distributed and shared memory parallelism. So all of the parallelization is taken away, and we do that automatically, as Carlos was talking about. For the Nemo API, at the moment, we're just concentrating on shared memory parallelism. So we assume the distributed memory parallelism is already in the code, which it is for Nemo. And another feature, I think, which is important, is that I come from an HPC background, and I still believe, whether I'm right or not, I don't know, but I still believe it's hard to beat a human. So one of the things, for example, we have to do is work around limitations and bugs in compilers and things like that. So sometimes you have to step in and do manual things. So what we do is rather than automating the approach of optimization, we encode those optimizations as a recipe in a Python script, essentially, and then those are layered onto the existing scientific source code to make optimized code. And the idea is you have different recipes for different architectures. So you still start off with the same source code, but you apply these optimizations to it to have different backend solutions. So this is a very high level view of the software. So as you can see on the left-hand side, we are currently Fortran in. And we have a number of APIs. I've mentioned the Elfric and the Nemo ones. They're the main ones we have. We also have one called Geocean, which is a 2D finite difference, finite volume API. And as you can see, we go into this intermediate representation. This is called the Cyclone intermediate representation, and we go from Fortran, we translate into that, and then we apply transformations to that, optimizations, and then once we finish with those, with that script, optimization script, we then can choose a backend. And the main one is Fortran at the moment. We're working on the OpenCL one, and there's something called SAR, which I'm going to mention in a second. So it's not a full crossbar at the moment. So for example, Elfric will just go into the Fortran backend. Geocean is the only one that goes into OpenCL, but the Nemo one goes into either the Fortran backend or the SIR one. And I'm going to start off by talking about the Fortran backend. So this work is done under Easy Ways 2, and it's been a collaboration with the MeteoSwiss and Hartree Centre, and which is us obviously, and NVIDIA. We're actually operating on unmodified Nemo code, and we're not going for a benchmark or a small snippet of code or anything like that. We're going for the full configuration. This is the standard MeteoSwiss configuration, Orca 1 SI3. It's a flavor that's particularly for the MeteoSwiss, that's the G08 part, but essentially it's a relatively standard Nemo configuration. And the picture you can see here is output from an NVIDIA tool. The top 2 lines, was it three lines, are what you get when you run this tool. It tells you how much time is spent on the GPU. So if you see the colors, then it means it's doing work. If you see white, then it means it's not doing anything. And you can see it's the full run. So the white bits at the beginning and at the end are the I/O. So, and you can kind of see a pattern. It's running for 10 time steps. Now you don't normally get any other output, but one of the advantages of a DSL is we can insert things into code. So so we've automatically inserted some profiling in for the CPU to see what's going on where for the CPU. So we can see when it's not doing things on the GPU, we can find out where that is. And that's automatically inserted. You don't change the code. So that's one advantage. And this is running on quite a large code. As Carlos said, they're large codes, 110,000 lines of code, 227 files. And the approach should be general. It should work on other configurations and versions, but we're only testing this one at the moment. It's also being evaluated by the Bureau of Meteorology. Whilst we call it the Nemo API, it is essentially a finite difference, finite volume stencil-based solution. So it's been evaluated for ROMs, and they've added OpenMP to the ROMs code there. And ECNWF are interested in it for adding OpenMP to Nemo, but that's just an interest at the moment. So at the moment, we're just going for relatively simple parallelization. As Carlos said, there are lots of different targets one could go. We're going for OpenACC kernels, which is about the simplest thing you could do. That just says, please, to the compiler, please parallelize this region. And we've been spending most of our time working on coverage and correctness. So it's just where to place them and finding out what parts, understanding the parts of code and where to put things. So understanding more complex structures like while loops and case statements, things like that. And what the script is doing is you might expect just to be able to put kernels at the top of a file and say, please do it. That doesn't work, unfortunately. So you have to find essentially the largest valid regions which contain loops. And they have to exclude certain things like certain types of arrays, derived types, write statements, things like that. Otherwise, the code won't compile, or you might get a bus error or segmentation fault, things like that. So this is essentially automatically inserting things into the right place to get it to work properly. And we insert quite a lot of kernels directives. It'd be a lot of effort to do that manually and find out where to do that. At the moment, it's just about correctness, really. We are going to look at much more optimization in the future. And the aim for us, really, I mean, Carlos has already shown performance improvement for his code. What we're trying to get to at the moment is just to see whether we can get the same performance as a CPU. Once we get to that kind of crossover, then we've demonstrated that it's at least as equally good to run on a GPU than a CPU. Of course, we want to try and beat that, but if we don't beat that, then there's no point in doing this in the first place. And this is kind of a timeline of where we're up to. So the left-hand side going up and down is runtime, so lower is better, is faster, and that is time in seconds. And along the bottom is how long is dates, basically from June up to roughly now. And you can see that we're getting faster with no change to the code itself. We've just been improving our solution, and you can see some things we've hit. So we have a relatively low-powered Skylake, which we've just gone past recently. But if we go for a high-powered Skylake, we're still essentially a factor of 2 away from that at the moment. So there's much more work to be done. But we are just doing the minimal insert at the moment. We really haven't gone in for a full optimization yet. But you can kind of see this evolutionary improvement in performance that we've been doing over time. So that was the Fortran backend. So the other thing is that we've been targeting is Carlos talked about intermediate representations. I think you may have got from his slides that they have an intermediate representation as well, which is different to ours. So what we looked at is how to translate from our intermediate representation into theirs. So what's the benefit of that? Well, if you put these two things together, so this is the same picture, just with if you look at the right-hand side, there's this SIR, which is the stencil intermediate representation. This is the precursor to the HIR that Carlos talked about. So this is what's there at the moment, and this will migrate to HIR. But at the moment, we're looking at the SIR, and then they have an optimizing backend called Dawn, which can target various different things, including GPUs with CUDA. So now for certain snippets of code, and we are only talking about snippets of code at the moment, we can start off with some Fortran code, and we can go into our intermediate representation and then translate into the SIR intermediate representation, and then go through and end up with C++ CUDA code or whatever Dawn does. So we started looking at this interoperability between these things. I think that's very important. If we can do that, then we can share tools and share optimizations and things. This also kind of potentially shows another idea that if you have a complex code, you may not, if an existing code, there are going to be regions where you can't really turn them all into, say, C++ and CUDA potentially. This allows us to then potentially target regions where we want to do the optimizations, and then part of it can be Fortran and part of it can be optimized for C++, and that allows us this migratory path towards DSLs that I've been talking about. And this is another picture. I mean, I've just shown how we can use their intermediate representation, but in theory, if we can share the intermediate representations, then the front ends that are SIR or HR front ends, GT Clang and things like that, and our front ends can all go into an intermediate representation, and then we can share backends. So that's kind of where we're looking at in this Easy Ways 2 European project that Carlos and I are working on. It's early days, but it's showing quite a lot of promise. So lastly, Italo asked me to talk about potentially some ideas of the future. I'll just do the first three, and you can just look at the last ones. But so I think from our perspective, what we're trying to do is demonstrate that DSLs can work on full codes in the near future, and we're pushing for NeMo on GPU. Obviously, we could do CPUs as well and OpenMP, but the fact that NeMo doesn't run on GPUs at the moment will show a kind of a big win. So demonstrating that, and also there's this other Elfric model I talked about very briefly, and we're looking to demonstrate that can work on pre-exascale and exascale machines as well. So we're looking to demonstrate DSLs on full codes. And of course, we're very early days on comparing approaches. There are a number of DSLs and programming languages and things. And I think, as Carlos also said, there are various dwarves, and the NeMo dwarf is a good one that will allow us to see the benefits and disadvantages of the different approaches, and then we'll be able to understand better how to take things forward. And as I said before, investigating interoperability between DSLs is it's a big thing, I think. And again, I think we'll probably do that through the dwarves. But once we can do intermediate representations, there may be other things that we could share. That's unclear at the moment. Okay, with that, I have finished. Thank you, and I shall pass back over to Italo.
Okay, Rupert, thank you so much for your clear presentation, and again, thanks for giving us this clear insight regarding the DSL words. Now, we can move to our question and answer session. We have 50 minutes for questions. I invite all our participants that are now are almost 60 to put and to post the presentation and to post the question by using the right panel or the GoToWebinar application. I will read your question to our speakers. So we have actually 3 questions. The first one is for Carlos and is from Bern again. And he refers to your example when you spoke about the MATLAB. We give just an example about MATLAB. And the question is that in Fortran, you can use transpose function. Does that give matrix awareness like MATLAB?
Right, so in that example, I chose it because it was simple, but it's true that also you can solve that problem via a different solution, which is calling a library. It's a very clear and well-defined problem, and then you can simply call a library, a library called as transposes matrix. Both are equivalent in terms of the semantic. In the example that I was showing, where you use a syntax of a programming language, B transpose, this quote transpose, and calling a library, making a library call to a transpose of the matrix, they carry the same semantic. And then internally, the DSL or the compiler or the library can apply the optimizations which are specific for the problem that you are trying to solve and for the architecture that you are dealing with. In our case, in weather and climate, unfortunately, we cannot use simply libraries because the problem has to be defined by the scientist. It's not like a matrix multiplication. And what do we do? The algorithm that needs to be solved is actually defined by the domain scientist, and this is out of our control. And there are many different solutions. There are many different methods, finite differences and finite volumes, discontinuous calculating, and so on. So we need to be flexible, and that's why we are opting for implementing programming language or DSL that carries this semantic that we can use later on.
Okay, so for the next question is a quick question for both of you. Are your DSL and tools open source? Is from Reinhard Young.
So is that Reinhard asking that question? So yes, our tools are open source. They're on GitHub. I think I flashed where they are up on the last slide. Yeah. So they are there. But yeah, if you just search, if you're interested, search for Cyclone, you should find it, and you can install it via pip. So yes, ours are.
Yeah.
Same in our case, all the software is open source. The projects are called Dawn, which is the compiler, and GTClan is the front end, and there is another front end within those projects being developed at DKRZ. It's still not open source, but everything that we develop is in the end. The aim is to make it open source and open development as well, so that people can actually contribute to it. It's really modular, so you can imagine contributing to a specific backends if you have a specific architecture. We focus a lot here, both of us, on GPS because there is quite a lot of interest in our domain, but anyone else can implement a different backend for different architectures.
Yeah, and I'll echo that. So there was a very small error in their backend, and that got integrated into their source code very quickly and efficiently. So, and we also have had external people contribute to us and fix things, issues, and it's a very powerful having an open source software. Okay,
the next question is from Andrea Russo. And he asked, did you evaluate Lisp and its metaprogramming capabilities for implementing DSLs? It's a pity that to use idiosyncratic languages like Python for such things.
Yeah. Okay. So Lisp. I have to admit, I don't have much experience of Lisp. I was in a computer science department for quite a long time, so I am aware of Lisp. And I know there are lots of Lisp champions out there. There are also people who find it very confusing. So I think it is a subjective thing. So we have chosen to use Python as our underlying language to do our DSL. And to be fair, we found it quite powerful, and I think the fact that so many people using Python is a big advantage. For some reason, I don't know why, it seems to have gained traction in the HPC world, whereas nothing else has. So I guess it's just, it's a practicalities really. I guess you want to do a Lisp implementation, I'm happy for you to do that, and we'll see how wonderful it is. That'd be great.
I also made the same comment, like in the picture and the slides that we show, we saw that it was totally modular. You can actually implement different front-end, and this is the idea of developing this intermediate representation, high-level intermediate representation. So this allows people to implement different front-ends if they provide different functionalities. I also tend to think that the programming language where the front-end is embedded is not so relevant, since in the end you provide a language with a syntax that you need to parse, and we just embed it in another language like Python or C++, just to be able to reuse some of the existing parsers already out there, since implementing a parser is quite hard. Even though I know, Rupert, probably you implement your own parser, but I guess you already reuse a lot of functionality from Python by embedding it into Python, right?
Yeah, it is a disadvantage going with Fortran. Obviously, the tool set is quite small, but no, there was already a parser out there, which we are now supporting, but it was already an implementation based on F2Py, which was some work done by another person. But you are quite right. The community in Fortran is a lot smaller than C++.
Okay, let's proceed with the next one. We have about 5 other questions that arrived. And the next one is from Jonathan Di Maia. The question is, is it easy to implement stochastic physics with DSL?
I don't know, well, I can go for it. Basically, it's about defining what your problem is, and right now we don't support it, but simply because we are constraining the domain to what we do in our weather and climate model. So the process, the way it works is we go to the existing model, how they implement the solutions, we identify the computational patterns. As I explained, many of them are stencils, and we also have vertical solvers, and this is what we use to constrain what we are going to put in our domain. The more general we go, you can also go general, but you might also end up in being a general purpose language and compiler. And this is also going to introduce some difficulties in dealing with optimizations and safety of the code and so on. So this is the main reason why we restrict to our domain. And so far, I would say yes. I mean, you can do it, but it's probably a different domain than what we are targeting.
And I echo that. Obviously, we've been trying to go with existing code as well, and Elfric, for example, is an atmosphere model which does include physics, and Cyclone is being used to at the high level for that. But there are quite large lumps of code in there that we kind of just leave. So in a kind of a macro scale, yes, I think we can certainly look at physics, and I know some of them have stochastic processes in them. So I guess at some low level, yes, we can do something. But yeah, as Carlos said, in order to know fully about it and to go fully into supporting them, then we need to extend the domain. So there's a halfway house, but to get the full benefit, I think there's quite a lot of extension needed.
Okay, Tim Palmer is asking, I am interested in running models at reduced numerical precision, single precision or half precision. Can mixed precision be applied within the DSL framework?
So, hi Tim. So yes. In our case, because we're dealing with again with some existing code. So for Elfric, for example, the precision is being added, and so you can then we have the ability to transform the kernel code as well, so we can change the precision. So yes, that's a new feature that we're working on at the moment. But in theory, for existing code, yes. I know Carlos is going to say definitely yes for him, but for us with existing code, then we do have a way of doing that, yes. But it's relatively new.
Right, and would also add that you can do it since in the end you are code generating, so you can code generate a different component on a different position if you like. The integration is also up to you a little bit how to deal with that. But we are in our case not exploring yet much about it. Like what would be beautiful in the future is actually to identify what pieces might go into mixed positions and what not, and be able to, for example, do sensitivity analysis or uncertainty analysis automatically. Since we have full control, we can analyze the code, we can understand, reason about it. Perhaps we can interoperate our tools with some other uncertainty analysis that will tell us, give us some sensitivity of different parameters and tell us this actually component is suitable, or if you port this to mixed position, then you might have to be more careful. But I think, I don't know, any DSL effort that is still exploring that aspect, but I think there is a lot of potential in that direction.
Actually, I'd echo that. And one of the things we don't really talk about is what, once you have a DSL, the extra things you can do, and it really does give you flexibility to, and you can change things across the whole code very quickly, and so it allows you to then try out lots of things like changing precision as well. So it can be considered to be like a tool to help you do an investigation into those.
Okay, we have to go quickly because the time is running up. So the next question is from Euberto Ricayan. How can we portray best system thinking and modeling for waste to energy project implementation and to be included somehow in energy, water, food, healthcare, environment nexus?
Sorry, I didn't understand. Can you rephrase, or I'm not sure if Rupert understood the question?
Yes, he's asking how to portray the best system and modeling to energy project implementation.
So is this for a specific code that they have? They're interested in how they might use the system?
Yeah.
I guess from our perspective, it needs to be a code that has the structure we're supporting. So if it has the characteristics that we support in our DSL, then I think the thing to do is to contact one of us or to try things out and then contact one of us and see what can be done. We're obviously very happy. I guess you'll give our email addresses out or something, or people can get those. And if people want to ask us afterwards, I'm sure Carlos and I will be very happy to talk about things offline. But it's very hard to say for a specific code yes, no, because it it depends on what's in the code. So I think if it's a stencil-based code, then and a finite volume, then Carlos would say yes, and we'd probably say yes as well.
Yeah, exactly. Unfortunately, the examples are probably not in the repositories, are in our case, because the full examples are the models, and the models are under license. So this is where, if someone else is interested, we should discuss and analyze if the patterns that they have in their model are equivalent or similar to the ones we are dealing with.
Yeah, we have documentation and some examples which may steer you in the right direction, but I think when it comes to a full code, it's best to ask and talk to people about it.
Okay, the next question is from Matthew Leclerc, who is saying, suppose we start using DSLs, how do we continue developing projects on the side of this big code, like for instance, coupling models?
Mm-hmm.
So I can talk for the Met Office and their Elfric model. They are using our DSL, and they are starting to couple using Oasis to Nemo, and they're looking at that. And I think from my perspective, a DSL is a kind of within a model optimization. I mean, you can think of it bigger and you can optimize, but so all you need to do is make sure that the hooks are there for being able to do coupling as well. From our point of view, again, because we have the top level algorithm is actually written in Fortran. You can add in Oasis calls, or you can do other systems. So it's kind of relatively easier to do that integration. I guess you'd have to extend Carlos' stuff, but he'll talk about that.
Right, and this is a really good question, since we are all figuring out at the moment, since we are like coming from small doors where we are demonstrating our DSLs into more full models and full pieces or component of the model. So this is a big question, how to integrate, and there are different ways. One is clearly to just integrate a DSL component, could be a dynamical core, or could be a physical parameterization into an existing model. And if the DSL generates some other code like OpenSSE or CUDA code, then we need to make sure that the data layouts, for example, or the arrays, the Fortran arrays are compatible, or trigger copies automatically to go from one component to another component. But still, we need this intermediate layer, this wrapper that is connecting the DSL generated code and the rest of the model, or maybe an existing model. And maybe in the future, as we go about it, we can integrate more and more components of a model, and then we'll learn and we'll figure out how to do this more properly until we don't know what's going to happen. It could be that eventually the model is entirely written in a new framework in the future, or it might be that it's still the model, the driver of the model and the coupling system, and so it stays where it is today, and we just pour like computationally expensive part of the model to the DSL. That I would argue that we need to learn all together.
And I think taking a bigger picture as well, that was one of my points on my last future look slides, is at the moment we treat different levels of parallelization in different ways. Essentially, coupling is very large grain tasking, and what we're doing is we're doing kind of middle size tasking, and at the lowest level you can have very fine grained tasking. And I think in the very long term, I think some way of integrating these so that we can treat them in a what does that mean? Sorry, we can treat those in a more integrated way in the long term. I think that would be much more powerful rather than treating them as separate levels of parallelization.
Okay, so we are for the last questions is from Milan Clower. The question is, the DSL solution that both of you presented involve many layers of different languages, which may be more accessible at the front end, but make it difficult to implement changes in lower layers. What is your opinion on the Julia language, which claims to have solved the two language problem? And he refers to the Klima project.
So I think the Julia language per se is a language is not solving. I think we are talking about different things probably. I know that there are people doing this kind of things, so DSLs implemented in Julia, since Julia allows you to implement a model that is going to take the user code and can do some transformation. Nevertheless, I think our DSLs, they go beyond that, since they can, for example, understand that you are in a domain and you know how you can do data dependencies, since it also understands the parallel model that you are dealing with underneath, and it can do fusion, and it can do data locality improvements, and so they are not only basic transformations, but they look across an entire component like a dynamical core, and it can apply all these optimizations, since it retains all the semantic of everything that happening to your model. Certainly, you can use Julia in the graph that I show. Again, there were different frontends, and Julia can be a very nice frontend, since it allows you to provide a very concise and very high-level frontend for the user to program with, and very interactive. So certainly, it's a possibility. We are still not exploring, but it's a possibility in the future. But I tend to think that we still need, nevertheless, more this compiler underneath, and not just a simple transformation model that Julia allows you to just do one kernel, and we are going to port that kernel into GPUs, since again we are looking across more like an entire component of the model.
Yeah, I have nothing to add to that. That's a great answer, Carlos.
Okay, I would like to thank all of the participants. I thank also the Carlos and Rupert for the presentation. And before closing the webinar, I just give you a quick advice for the forthcoming webinar. The next one will be held 5th of December, and it will about the handling soil loss hazard through Copernicus data and tools. All the webinars are also recorded and published into the CMCC YouTube channel. You have here the reference to access the webinar offline.
Thanks again, and see you next time around. Bye bye.
Thank you very much.
Thank you.
Bye bye.
Thank you. Bye bye.